Welcome back. Let me congratulate you for making through week 6 and solving all assignments of week 6. Today we are entering week 7 where I will introduce you to one magic tool which is called moment generating function, and it will magically take care of many of the hurdles that we faced in weeks 5 and 6. Okay, so let us set the context why we are studying this tool. So in week 5 we studied convolution and we ended up in having very cumbersome integrals like sum of two normals. We are essentially multiplying two normal densities, whereas it is very difficult to handle those two densities in a calculus way. Okay, so that is where we were landing up in cumbersome integral. Then in the last week, in that problem solving drill, we computed compound variance, and it took long, and even if we had this law of total variance, it was slightly time consuming. Okay, though it solved our problem, but it was time consuming. So the core issue here is all our hardest problems are involving sums of random variables or random sums of random variables, and we need a better, simpler and so called magical tool. Is there any such tool? The answer is affirmative. Yes, there is a tool, but it requires some different kind of variation, and that tool is called moment generating function. We will see why this tool will is named like this, moment generating function. It has some connection with moments of the random variables, but the main idea of this function is, in some sense, when I am handling in the PMFs or PDFs, I am having a difficulty because of the detailedness of those PDFs, okay, or PMFs, and therefore I need not look at each and every value of these. What I need to do is I need to get this everything summed up in one function, and that is what that function will transform these PMFs to a different dimension. It's similar to what we studied in Laplace transform or Fourier transform while studying ordinary differential equations. So we want to encode the knowledge of the distribution into another function which is a transform of that distribution. So that tool is MGF. So how will we do that? That is where we are using this magic strategy. So you have PMF and PDF. These are hard problems to handle. So what we will do, we will use this tool, we will apply this tool, and suddenly it becomes easier MGF problem. What we will do, once we apply this MGF technique, the problem will be transferred to MGF world, and in that MGF world we will appeal to the uniqueness of MGF for identifying the probability distribution, and then we will solve in MGF world, guess what that distribution is in our PDF world. So this is the idea, and graphically it can be represented like this. So PDF PMF world on the left hand side, it's hard because we need to have this convolution, and it requires kind of calculus. Now what we will do, we will take the transform of this using our law of unconscious statistician. We will define mxt to be equal to expected value of e raised to tx. We will define it formally. We will take this into MGF world. Now this z equal to x plus y, because of the mere fact that this particular transform raises everything into exponent, okay, everything becomes a multiplication problem or division problem, okay, because of this particular structure, and then I can solve it using algebra. I need not use any calculus, and when I solve it I will get the solution in the MGF world. I will recognize the distribution via proving uniqueness of this MGF with PDF PMF world, and then I have identified the respective PMF. Okay. So this is the idea. So let us begin our journey by developing a necessary theory for defining this transform called moment generating function. Give me any random variable x, I will multiply it with some parameter t in the parametric form and I will raise it to the exponent. So, e raised to tx is the new transform that I have, and then I will ask for expected value of this transform. Okay. So, what are the important inherent salient features of this e raised to tx? First of all, you all know this exponential function is a monotone function. So, it preserves the properties of x. Because it is raised to the power of exponent, I am getting rid of all negative values. Okay. This particular thing will be in the positive domain. Okay. And then I have expectation, so it will behave nicely. These are the important features of this MGF. So, how can I apply this to our discrete and continuous world? The corresponding formulations can be given like this, where we are essentially applying nothing more than lotus, and t is a separate free parameter that I have, which I will exploit, by the way, which I will exploit to find certain good things from this particular transform. Okay. So, mxt is summation over all x's e raised to tx probability mass function of x. If I look in the continuous world, it is integral e raised to tx fx dx. So, now we have from the world of fx, because we are integrating out x or we are summing over x, we are mapping everything into the world of t. Okay. So, that is why it is called transform. So, it is mapping from the x world to the t world. So, we have new variable which is t. Okay. So, now I will use the power of this particular t and show you why this particular function is called moment generating function. So, the answer is this particular function, we claim that it is a generator of the moments. What are moments? Expected value of x, expected value of x square, x cube, all integer powers that we can think of are moments of the distribution. Okay. So, now we claim that this particular function mxt actually generates the moments. How they generate? By using calculus. You just differentiate this function with respect to t and then equate the value at t equal to 0, you get the first moment. If you want to consider the kth moment, you just differentiate this function k times and then put the value of t to be equal to 0 at that kth derivative and you get the kth moment. Okay, let us try to show this for the first moment. So, I have mxt, correct. What is mxt actually? If its expected value of e raised to tx, correct. So, if I take derivative of this value, now derivative, because I am in the t domain, right. So, I have to take the derivative with respect to t of mxt. I am essentially taking derivative of expected value of e raised to tx. Okay. Now, expected value is either a sum or an integral. Because this particular function is finite and there is a law of derivative under integral sign, I can pass this derivative inside the expectation, and if you agree to that, then it is very easy to understand that this is nothing but d dt of e raised to tx. Okay. So, it requires some technical argument to pass this derivative, but assume that argument is true. Okay. So, now we are simply dealing with derivative of an exponential. So, what will it be? Derivative of exponential, as you know, is going to be e raised to tx as it is into derivative of tx, that will fetch me x. Okay. So, x e raised to tx. Okay. So, this is what I will get. Now, what we said, evaluate this at t is equal to 0. So, I will put evaluation at t equal to 0 for all of them. Okay. Then when I put evaluation at t equal to 0, what is the value of e raised to 0? It is 1, right. So, I get expected value of x. Okay. Now, if you are not satisfied with this, this is basically I have taken m x dash at 0, right. If you are not satisfied with this and you want to check further, you can check further. If you want to take the second derivative of this, which is derivative m x dash t, you differentiate it again d dt, then you are essentially saying you are taking a derivative of this x e raised to tx, right. So, you can easily do that and you will see that this is expected value of x will be thrown out because I am taking the derivative, again d dt of e raised to tx, correct. And then again for the same reason, this will become expected value of x into x, so x square e raised to tx, and again I say evaluate it at t is equal to 0, t is equal to 0, t is equal to 0, what I got? I got expected value of x square. So, you can do this for any value of k, you keep on differentiating, you are essentially saying you are getting the moments back. Okay. Okay. So, now the power is, once I have this closed form expression of this MGF, I do not have to worry about density to calculate these moments, otherwise all these are complicated integrals. Here simply you differentiate, it will solve your problem, and you are differentiating with respect to t. So, you do not have to deal with complexes of x world, okay, that is the beauty. So, let us review what I have done. For k equal to 1, what I did, I started with definition of moment generating function, differentiated it, passed expectation and derivative inside out. Then I used the chain rule, set t equal to 0 and got this expression. I have also shown how mx double dash of 0 is expected value of x square, and if you continue like this for kth moment, you will get the kth moment. So, the beauty is, in one shot you are getting all the moments, that is the first thing. Let us apply this to some of the problems and find some moments of some standard distributions. Okay. So, I have a random variable x, it is given that it has moment generating function 1 upon 1 minus 2t, and you are asked to find mean and variance. I know how to compute mean and variance given the density, but now I have to compute mean and variance using MGF. How easy it is, let us see. So, what is our answer? So, expected value of x, if I want to compute, it will be mx dash of 0, right. So, essentially I have to compute d dt of mx t, that is d dt of 1 upon 1 minus 2t. So, what will it be? It will be 1 minus 2t raised to minus 1, minus 1 minus 1. So, minus 1 upon 1 minus 2t the whole squared multiplied by minus 2, right. So, it will become 2 upon 1 minus 2t squared. What should I feed in? I need to feed in t is equal to 0, t is equal to 0. So, if I feed that value in t is equal to 0, what I am getting here? This is going to be 0, so it is 1, so it is, the answer is 2. Okay. Can I compute variance? Yes, I can actually, but I have to compute expected value of x squared first, which is mx double dash of 0, right. How will I compute? I already have the answer for mx dash. So I will again use mx double dash of t is equal to d dt of mx dash of t, which is 2 upon 1 minus 2t squared. Okay. So what will this be? First 2 will be thrown out, and it is derivative of 1 minus 2t squared, 1 upon 1 minus 2t squared. So it will be 1 minus 2t raised to minus 3, okay, into minus 2, and then one more thing will come, because it's minus 2 of this and 2 of this, minus 2 of that other thing. Okay, so 1 minus 2 comes from 1 minus 2t square, that minus 2 is there. So minus 2 times 1 minus 2t cube, and 1 minus 2 comes from the derivative of minus 2t that I have taken. Okay. So all these together will give me 8 upon 1 minus 2t the whole cube. Now I will substitute given t is equal to 0, right. So what will this give me? Given t is equal to 0, this should be 8. So I got expected value of x squared to be 8. So what is variance of x? Is 8 minus 2 squared, which is 4. So the variance of x is 4. Okay. So mean and variance both are through moment generating function. Okay. So this is expected value of x. I have already shown, this is clean printed version of the solution, and variance of x, which is 4. Correct. So we have understood how to use moment generating function to calculate the moments, and the calculation is very easy, because you just have to deal with appropriate differentiation rather than integral. Okay, let us take one problem in the discrete world, where I have a very simple random variable. Probability of x is equal to 1 is 0.3, probability of x is equal to 2 is 0.7. I want to find MGF of this. Oh, this is very easy, because what is my MGF? I simply have to apply that definition, right. So it's expected value of e raised to tx, correct. Now I know my x takes the values 1 and 2, for all other values it is 0. So it's basically e raised to t into 1 into probability of x equal to 1 plus e raised to t into 2 into probability of x equal to 2, correct. So I will simply substitute, this is e raised to t, probability of x equal to 1 is 0.3 plus e raised to 2t into probability of x equal to 2 is 0.7. That is all. So I have the answer, right. So it becomes e raised to t, t plus t, so 2t, so the into 0.3 plus 0.7 e raised to t. Okay, that is my answer. Okay. So that is very easy. So we can easily compute this particular thing. If you do not take e raised to t common, this will be your answer. Okay. Now what? Now you can also ask, since I have figured out MGF, let us actually see computing expectation is easy from MGF or PMF, because I have PMF as well, right. So let us do the comparative analysis of both. So here is the method. So in this case, because it is discrete, I have 1 and 2. So I will just simply put those values, and I get the answer to be 0.3 plus 1.4, 1.7. Here you have to just differentiate and then put the value to be equal to 0. So in that case you are also getting the same answer. It is just 2 steps. So both, in the simplest case, the A's is more or less same, because you have to just differentiate and get the answer, but you have to also look at the fact that the distribution is very simple. Okay. Now about establishing one-to-one correspondence between PMF and MGF. What can I say? If I have been given this PMF, whatever MGF that I have figured out, is it unique or not? That question we need to answer. So to answer that question, let us prove this uniqueness property. Okay. So we have, whenever MGF exists in the neighborhood of t equal to 0, MGF uniquely determines the distribution, and there is a one-to-one mapping between MGF and PDF or PMF. Okay. Okay, I said I will prove, but proving is really a cumbersome exercise. Let us assume this property and use this property in all our problems. So whenever I say mxt is equal to myt for all t in some interval around 0, then x and y will have the same distribution. I can give you the glimpse of the proof so that I am not giving some hand waving arguments. Let us say mxt is equal to myt. Then this means expected value of e raised to tx is equal to expected value of e raised to ty. Okay. So now I am assuming, without loss of any generality, this is a continuous integral. So in that case, this implies integral from minus infinity to infinity e raised to tx fx dx is equal to integral from minus infinity to infinity e raised to ty fy dy, correct. And now if I consider this in fact implies my, if I take this right hand side on the left hand side and combine all these integrals, then replace this x. So this, let us say this is fxx, this is fyy. Okay. So now these integrals have dummy variables, so I will combine them. So it's basically e raised to tx fxx dx minus integral e raised to ty fyy dy from minus infinity to infinity, both are there, is equal to 0. Now this x and y are dummy variable. So what if I replace this with x? It does not matter, right? I can replace this with x and this will be integrated over x. Okay. Now can I combine these? What is different is this fx and fy, right? So that implies integral over minus infinity to infinity e raised to tx. E raised to tx is common to both, fxx minus fyx dx must be equal to 0. Okay. Now somehow using some analysis arguments, I have to argue that this number fxx minus fyx is equal to 0. Can I do that? So for that I need to use some monotonicity property of this function e raised to tx and say that this number, if this integral has to be 0, then the only term that has to be 0 is this term. Okay. And for that I will use some calculus arguments and show that this fxx is equal to fyx for all x's. And if I show that, then I have established the uniqueness property of this particular moment generating function. If fxx is equal to fyx, then it is by default clear that mxt is equal to myt. So, this I will not prove because it uses heavy calculus. So, I will not prove that, but assume that this is going to be true. Okay. So, we have dealt with uniqueness property. Let us understand how to use this in practice. So, for example, if somebody gives you mzt is 0.8 divided by 0.8 minus t, okay. Do we need to invert this to get the PDF? No, we will not do that. What we will do is, we will use this and we will recognize it with MGF of some standard distribution. And once we have that establishment, then I can readily identify this particular thing is MGF of exponential distribution, and then I will recognize the parameter. So, then once you identify this MGF as MGF of certain distribution, it just becomes a pattern recognition problem. So, for that we need to actually understand how the parameters of our standard distributions are connected with MGF. So, this is a table which we will plan to derive, which we will derive in the next class, and we will have exact mastery over recognition game. We will have this MGF lookup table handy for ourselves, right. So, let us summarize what we have done today, and we have introduced a new transform from random variables, and we call that as moment generating function. A systematic way to obtain moments is taking the derivative and substituting t is equal to 0, you will get all the moments that you can think of. Okay. So, now when we introduce this transform, we learned some tools. So, what are the magic properties? First, I can generate any moment now using this technique, any integer moment I can generate using this technique. I also know that if I am able to remember certain standard MGFs, I have a one-to-one correspondence between random variables distribution and MGF. So, I can easily identify distribution by lookup and recognize method, for which we need to develop mastery over that lookup table, and that is our agenda for the next lecture. That is, we will use MGF lookup table for all our name distributions, and then in the next class, next to that class, we will actually apply this to tame the sums of random variables problem and random sums of random variable problem. Okay, so that concludes this particular lecture. Thank you.